Alright, good evening everyone. Per your request, I have made an integration flow chart. So, follow along with me if you will. We'll start at the start. Question 1. Do you have to do an integral? If no, there's no integration to do. You're done integrating. So the flow chart was very simple in this case. But if you do have to do an integral, we'll proceed over to the right. And the basic principle of this flow chart is look for the easiest thing to do first. If the integral is easy, do the easiest possible thing. And then just kind of work your way up through the more difficult ideas. So this is just the way that I think about doing integration. I'm not saying this is the way that you should think about it, but I do think that you should try to follow that principle. Think about, or maybe even make a list of the techniques of integration. Think about which are the easiest for you, and then start with the easiest and then work up to the hardest. Okay, so the first thing I check is, do I recognize that the integrand is the derivative of some function that I know? If so, then whatever function I need to differentiate to get the integrand is the answer. Okay, so I write that down and I remember to put a plus c. If not, I proceed down the chart. Can I do some algebra so that the integrand is the derivative of a function I know? If so, then you should do that algebra and then hopefully recognize it as a derivative of a function you know. Okay. If I cannot do that algebra, then basically what we see here is I'm checking, can I do integration by substitution? Is one factor in the integrand the derivative of some other portion of the integrand? Particularly, sometimes it'll be the inside function of a composition, but sometimes we won't immediately see that. So I gave some examples over here on the right. Okay, if we look at this first example, I don't immediately see a composite function there. Okay, but we do recognize that the derivative of the numerator is 1 over 1 plus x squared, so this is going to be done by integration by substitution. Here we have kind of a more classic example. Composite function, inside function is x cubed, its derivative is 3x squared, so integration by substitution is what we're going to do. Okay. So if this happens, I do integration by substitution. And hopefully this concludes the problem. Okay, but if you find that you're not yet done after an integration by substitution, then just think about what kind of integrand are you looking at? How would you describe the integrand? In a productive way. If you would say the integrand stinks, the integrand is gross, I don't like the integrand, that's not helpful. Okay, so describe the integrand in some way that you can do something with it. It's a product of functions. We know that the rule for integration that tells us how to integrate a product of functions is integration by parts. Also, we learned that integration by parts is what we do if we're integrating just the inverse of some function. So like ln x is the inverse of e to the x, inverse sine x is of course the inverse of sine x. In this situation, we integrate by parts. We let u equal the inverse function and dv equals dx. If the function is a rational function, in other words, it's a quotient of two polynomials, even if it has one of these forms that appears to lend itself to a trig substitution, I make an effort to use partial fractions. Okay, I may need to factor the denominator, and then it's the standard partial fractions type of exercise. Get the partial fraction decomposition, and you should know, certainly, as I said, I'm going to ask it on the test on Tuesday, how to integrate every term in a partial fraction decomposition. That's the whole point of it. Okay. If it's none of these things, you might say, well, I recognize the integrand has some composite function, but integration by substitution doesn't seem to be working. Here's an example. We did one like this. Suppose I had e to the square root of x. It's a composite function, but its derivative doesn't appear anywhere in the integrand. Whenever you have a composite function, generally integration by substitution is going to do something good for you. Okay, so if you let, this may be an example you want to try. If you let w equal the square root of x, you'll see that it changes the integrand into something that you can integrate by parts. If you still haven't found it, you might say it has some square roots in it that are problematic. It makes the integration hard. And then you should think, does a trig sub help? There are certain forms for which a trig substitution is helpful. X squared plus a squared calls for the substitution x equals a tangent theta. X squared minus a squared calls for the substitution x equals a secant theta. and a squared minus x squared calls for the substitution x equals a sine theta. Okay? Or there's this Forster way to do it, as he describes in the book, where he makes the triangle first, and then all of the terms in the integrand can be expressed in terms of ratios of side lengths of this triangle. Then the trig substitution converts your integral into a trig integral, and I'm anticipating you know how to do that. We took notes on that, so I don't recap that in the flowchart. If a trig substitution helps, then do a trig substitution, and then when you have done a trig substitution and done the trig integral, you will be done integrating. That's good. If a trig substitution doesn't work, you know, maybe we're kind of at the end of the flowchart, as you can start to see. Okay, are you sure that you cannot do a regular substitution? Maybe you overlooked that. No, I'm not sure. Well, just check. Okay, maybe if you make a substitution, I mean, you have some kind of problematic square root, so there's something under it that's not just x. So that's a composite function. So maybe you can let w equal what's under the square root and something good happens. Okay, or it's possible I gave you an integral that you can't do. If you're sure a regular substitution won't help, and if I gave you one you can't do, then you're done integrating. Okay, but I think I'm going to be able to find integrals that you can do for the test on Tuesday. This covers, and this is not universal, there's probably some things that I'm overlooking, but if you are comfortable with all the techniques that are described in this flowchart and you basically recognize the patterns that are described in this flowchart, you should be in good shape. Should be in good shape. Okay. What I also did, here's your flowchart. I'm going to upload this online. You can view it at your convenience in full rather than just in parts. I guess I could have changed the size, but for the video it'll work well that everything is bigger. What I have here is, on the next sheet I have 5 integrals, and we're not going to do them, okay, but what I want you to do is just think about what would you do to do them. And we're going to look at each integral one at a time, and I suggest that you pause the video for just a few seconds as necessary as you look at each integral to just ask yourself, what would you do to do this integral? So here we see integral number 1, and I ask you to think about what would you do to do this integral. So again, pause the video for a few seconds, and then I'll give the answer. This first integral is done by dividing every term in the numerator by the square root of x and splitting this up into 3 fractions, each of which is just a power of x, so you know how to integrate it. So in the flowchart, this example would fall under the example of, can you do some algebra so that you recognize this as the derivative of something? Do the algebra, then integrate. Question 2, how would you do this integral? Pause and think. Integrand has a composite function. Okay. If I make the substitution w equals e to the x, its derivative is another part of the integrand. So this integral will be done by substitution. Integral 3. Pause and think. It can be done by a trig sub. It will be easier to do partial fractions. The denominator factors into 3 minus x times 3 plus x. So it has a simple partial fraction decomposition, a over 3 minus x plus b over 3 plus x. You find the constants, you integrate. Easier than a trig sub, in my opinion. Integral 4, pause and think. It's an inverse function, you integrate by parts. Let u equal inverse cosine x. dv will equal dx, and then after you integrate by parts, you're going to get an integral that's done by substitution. Work through it. If you're not sure, you could do it, as with everything. Integral 5, how would you do it? Pause and think. We have this exponent. It's not a rational function, okay, because the exponent in the denominator is not an integer, so the denominator is not a polynomial. So partial fractions is not going to work here. This fact that there's a half integer in the exponent, okay, I have this division by 2, means that really I have the square root of x squared minus 9 raised to the 5th power. Okay, so since I have the square root of x squared minus 9, it's in a situation where a trig substitution is going to help. Okay, I'm considering this question to be a challenge question. It's not super hard, but on a 1 to 10, maybe it's an 8. So I'm going to consider it a challenge question, and since you were kind enough to watch this video all the way to the finish, if you do this question and give me a complete solution with an exact numerical answer, so I know that you can check it on a computational engine, but I want an exact numerical answer to this question. If you give that to me at any point next week, which is the week of February 23rd, I will give you, let's say, 4 additional percentage points on your test on Tuesday. Thanks for watching the video. I hope that it was helpful. Let me know if you have any questions. And of course, you know, if you want to do these integrals for practice, the more practice that you have time to do, the better. I encourage you to do them, and you can check your solutions on wolframalpha.com. That is a great thing to do for yourself always. Thanks, guys. See you Monday.